Welcome to this video lecture. My name is Vlad Sedláček, and I will be your guide into the realm of elliptic curve cryptography, or ECC for short. I divided the lecture for 3 parts for easier orientation. In the first part, we will be concerned with the arithmetic of elliptic curves. In the second one, we will go a little bit deeper, and in the third, final part, we will see some bonus material. Let's start with some history. Elliptic curves have first been described by Diophantus in the ancient Greece. Later, they were studied by many more mathematicians, and recently they have even been used as a key ingredient in the proof of Fermat's last theorem, a very famous statement in number theory. The name elliptic refers to certain integrals that measure the length of the arc of an ellipse, because such integrals use functions that also define elliptic curves. We will see those in a moment. Probably the first practical application of elliptic curves was a factorization method by Lenstra. This method is still useful today. This was in 1984, and only a year later, Koblitz and Miller proposed ECC. It was already known that the discrete logarithm problem can be defined in different groups. So they thought, why not take the group of points on an elliptic curve? And indeed, this turned out to be very efficient. It resulted in small keys and very fast computations, which is great for small devices. More concretely, if you take 256-bit ECC and 3072-bit RSA, they are estimated to both offer 128-bit security. So you can see quite big savings with ECC compared to RSA. And nowadays, ECC is almost everywhere. It's used by the TLS and SSH protocols, which form the secure backbone of the internet, but also in our mobile phones, electronic documents issued by the government, cryptocurrencies, IoT, smart cards, and so on. Some of the most used protocols are ECDH, meaning elliptic curve Diffie-Hellman, ECDSA, elliptic curve digital signature algorithm, and EDDSA, Edwards digital signature algorithm. Before talking about elliptic curves, we need a small reminder on what a field is. Here you can see the formal definition, but you can think about a field as an algebraic structure which allows you to do basic arithmetic, meaning addition, subtraction, multiplication, and division by non-zero elements. If you want to see some examples, the common ones for infinite fields are the rational numbers, the real numbers, and the complex numbers. But we also have examples of finite fields. And in fact, for any prime number p and its power, there is exactly one field with p to the n elements up to isomorphism. We denote this field f p to the n. You should be familiar with the set Zp of integers modulo the prime number p, and when n equals 1, we have fp equals Zp as sets. But this is not true for n larger than 1, so be careful with this. But luckily, in cryptography and mostly in this lecture, we will only work with fp, which is the same thing as Zp. And in the last lecture, we have already seen the discrete logarithm problem, or DLP, in at least 2 types of groups, the additive group of fp and the multiplicative group, fp star. In a moment, we will see how this can be generalized into the group of an elliptic curve. Alright, now we are ready for the main definition of this lecture. There are several different definitions of elliptic curves in fact, but in order to avoid projective and algebraic geometry, we will go with quite a simple version. So let f be any field and choose 2 coefficients a and b from the field, such that a certain expression is non-zero. Then an elliptic curve over f is the set of pairs xy coming from the field that satisfy the Weierstrass equation y squared equals a cubic polynomial in X. These points are often called the affine points because we also add one other special point O, which we call the point at infinity. But don't worry, there's nothing mystical about it. And in cryptography, as I said before, we are usually interested in the case where the field is Fp, where p is a prime number, often a quite huge prime number. Also, whenever you see an orange text in these slides, you can feel free to mostly ignore it, but if you wanted to seek some deeper understanding and wanted to use the slides as a reference, just be aware that the orange text is often simplified for the purposes of easier exposition. Now it's time to see some pretty pictures. On this slide, we have elliptic curves over the real numbers, parameterized by a and b. In some cases, you can see they have two different components, whereas in other cases they have only a single one. Actually, in one case, the curve we get is not elliptic, but more on that later. Also, if you noticed, in the Weierstrass equation we have y squared. And this implies that xy is a point on the curve if and only if x minus y is a point on the curve. And in the picture you can see this leads to a nice symmetry along the x-axis. Moving on, here we can see an elliptic curve over the complex numbers. And as you see, things have changed quite dramatically compared to the real numbers, because in this case, the elliptic curve can actually be viewed as a torus. This is a quite surprising fact, but unfortunately, its proof is well beyond the scope of this lecture. And finally, here you can see an example of an elliptic curve over a finite field. The symmetry is still present, but you can see that the discretization has destroyed the nice shape that we were seeing before. For this reason, it might be useful to visualize the image of an elliptic curve over the real numbers, because, well, it is more intuitive when thinking in geometric terms. I promised you before that we will work with the group of points on an elliptic curve. But it's not immediately clear that the points form a group, so let's try to show that now. We will need a geometric fact that every line intersects an elliptic curve in exactly 3 points, at least if we count these intersections in the correct way. Thanks to this, we can now define the group law on an elliptic curve as follows. If we take two affine points, P and Q, we can draw the line connecting them, and thanks to the fact there is a third intersection of this line with the elliptic curve, we can take this intersection and mirror it along the x-axis, and that gives us a point R. And we can define the sum of P and Q to be this point R. We can also consider the special case when the points P and Q coincide. Then the secant connecting P and Q degenerates into a tangent at P. But we can proceed in exactly the same way. We draw the tangent at P to the elliptic curve, find the intersection with the curve, and mirror it again. That gives us P plus P, or we also call that 2 times P. Finally, we can consider the case of adding two affine points P and Q that lie on the same vertical line. It may seem that there is no third intersection, what can we do? But in fact, there is, and it is the point at infinity O, because you can think of O as the vertical direction, or put another way, you can think of it as a point that is very far on the y-axis, in fact, both at plus infinity and at minus infinity at the same time. It follows that O must be the neutral element of the group, because when you mirror O, you get O again. This also means that to compute the additive inverse of a point, you can simply mirror it. The group law might seem a little ad hoc, but in fact it comes from some quite advanced geometry. You can concisely summarize the whole group law by saying that it's equivalent to the statement that 3 points sum up to the neutral element O if and only if they lie on a straight line. It is also easy to see that the addition operation is commutative, so we have just defined an abelian group. While the geometric view is a nice way to understand the group law, it does not allow us to make computations, for example over the finite fields. For that, we need an algebraic approach. If we have two affine points P and Q given by their coordinates, it would be nice to be able to express the coordinates of their sum. So let's try to do that now. First, let us consider the case when the x-coordinates of P and Q are different. To describe the equation of the secant through P and Q, it's useful to compute the slope of this line. And we can express that as the difference of the y-coordinates over the difference of the x-coordinates. You might also want to look at the previous pictures during these computations. When we have the slope, we can express the equation of the secant just by shifting the line in a way that it will go through P. And by the line, I mean any line with slope m. So now we know that the equation of the secant is given by y equals m times x minus x1 plus y1. To find the intersection of this line with our elliptic curve, we can just plug this expression for y into the equation of the elliptic curve. To solve this equation for x, we can expand the left hand side and then put everything together. When we do that, we can see that the coefficient of x squared is minus m squared. And now it's time for the good old Vieta's formulas, which tell us that the sum of the three roots of this equation is exactly minus the quadratic coefficient, so m squared. And because we already know that x1 and x2 are roots of this equation, because they are the x-coordinates of points P and Q that lie both on the line and on the curve, it follows that we have x1 plus x2 plus x3 equals m squared. And we can express x3 from this. So now we are able to compute the y-coordinate of the intersection by plugging x3 into this secant equation. But recall that in order to compute the actual sum of P and Q, we must also mirror this intersection along the x-axis. And this corresponds to just flipping the sign of y3. So whenever you have two affine points P and Q that are distinct, you can compute their sum using these formulas here. Similarly, when the points P and Q coincide and do not lie on the x-line, we could proceed in the same way, only replacing the secant by the tangent, using some differential calculus. We will not do that here, but here you can see the formulas for the coordinates in that case. But notice that we still omitted a few cases that would result in a division by zero. When the x-coordinates of the 2 points are the same, but the y-coordinates are not, we are in the case where the slope of the line is vertical, so that we already know that the sum of the 2 points will be O, the point at infinity. This also means that to compute the negative of a point, you can simply flip the sign of its y-coordinate. When P and Q coincide, you can see that the slope of the tangent is vertical if and only if the y-coordinate is 0, thanks to the symmetry of the curve along the x-axis. In that case, 2 times P is O, the point at infinity, or put differently, P is the same thing as minus P. So now we have an algebraic way of adding any two affine points. The only remaining case is when at least one of the points is the point at infinity O, but then we can just proceed according to the group axioms, because O is the neutral element. So now we have managed to convert the geometry of the group law into algebraic formulas for all cases. The nice thing is that we can use these algebraic formulas over any field, in particular over finite fields that we will need. Just be aware that in practical implementations, it might be a little inconvenient to distinguish all the cases as we did here. This might lead to implementations being prone to mistakes, and these can sometimes have serious security implications. That's why in practice, you might want to choose another addition formula, and in fact, there are many different formulas to choose from. And just like in any group, once we have addition, we can iterate it to obtain scalar multiplication. This gets us to the underlying problem of most of ECC, the discrete logarithm problem, namely, given points p and k times p, find k. But just how hard is this problem? Well, let's find out in the next video.